Yeah, hello. So I will indeed walk you through the interaction proteomics exercise. And so that's the P3 interactions PDF document in the assignment folder. And so we're going to work on a pull-down data set. So publication is given here, which was a bit downsized from what is actually done in the publication, so that it's a bit more handleable in the session here. And so it's in yeast, GFP tech proteins, and then it's a couple of baits, I don't know, on the order of 15, 20 or something like this that we're going to analyze. And so they were done in quadruplicates. And so the way we analyze it is basically that we use, so if we want to know the interactors for one pull down, that we use all the other pull downs as the reference for that basically, right? And do then the test on the t-test between one pull down and the complement in the data set to that, right? And so I will just go through and do the things here in front, and you do the things on your laptops as well if you want, or you just watch, whatever you prefer. So let's start the software. That's always good. So content, software, Perseus. Start it. Here it is. Let's make it big. And now we start with loading the data. So that's here generic matrix upload. So we do that. Then we have to select the file. So that would be in practical, so data, practical 3 it is, I think. And there is this protein groups file, Keilhauer et al. So that is what a typical protein groups file would look like from a max quant output, where you have run all of these pull downs, and let's just load it. So, and as you see, so it's actually nothing left in this field here. So it has already, by default, sorted all of the columns into the right type, basically, right into main type. So all the LFQ intensities went into the main type. The ones that are the remaining ones that are numerical went into numerical, and so on, right? So you basically don't need to do much here, except for pressing OK. And there you have the data matrix. So now first you have to do these typical exercises that you also did for the normal proteome type of data, which is filtering a couple of things that you don't want to have in your matrix. So for example, the contaminants and the reverse hits you want to get rid of. So that's you do by going to annotation columns, filter rows. Filter rows. Here. Filter rows based on categorical column. And then, for example, only identified by site we want to get rid of. Right, so let's start with that. Only identified by site. If the value is a cross or a plus, then we remove the matching rows and we reduce the matrix. So then we do that. And so how did it change? So from 2401, we went down to 2353 proteins. We also want to get rid of contaminants still, so filter rows based on categorical column. Contaminant, for example, we want to get rid of. Same thing. Now we're down to from 2352 to 2326, and also the reverse ones don't really make sense to analyze, so let's get rid of those as well. Filter rows based on categorical column, reverse, let's get rid of them, and we have 2304 proteins left. Okay, so that's the set of proteins that we want to work with. So next thing is, so you always have to logarithmize the data before you work with other statistical tools on them. So let's do that. So you can use this shortcut button here. It's already filled out with log2. So again, here the base of the logarithm would really matter. So let's take 2. Why not? And now we have logarithmized data. So next is filtering for valid values. And so in many occasions, and in particular for pull downs, a good filter is that you require that in at least one of the groups you have good measurements. For maybe all of them or all but one in one of the groups should be measured. But of course, before we can apply this kind of filtering, we first have to have groups defined, which we haven't yet. So now first thing we do is define this grouping of quadruplicates that was done. So let's define the quadruplicates, and that you do by annotation columns, because you want to add the column with annotation about the samples, right? So we go to annotation columns, and we add annotation. We add. Oh, it's in. Is it in what? Oh, sorry, it's annotation rows, of course, because what we want to add is a row, basically, which has information about the columns, right? Just checking if you're listening. So. And then we want to categorical annotation rows, and we want to create one. And so one way you could create one is basically by just filling out all these fields. So what you see here is basically for each of the LFQ columns that we have loaded, you have now one entry here, and you could now for each column you could specify what is the group that it belongs to. So for example, we would just remove all of the underscore 01, 02, 03, 04, then we would have group names that would exactly subdivide everything into these quadruplicate groups, right? But that's a long list, so that's a bit tedious. So you can also define these with regular expressions. So that's here create from experiment name, and then so it's actually, you could do it with regular expressions, but it's already set up that basically it recognizes that you have endings like this, underscore, and then a number, and it would make the grouping out of this, basically. So let's try that. Yeah, so now it did the grouping, but so now I also realize it's probably better to first rename the columns and then define the grouping, as it is also written in the PDF that I was showing you, basically, right? Maybe I should read it before I do this here. So, but so I mean, then you just see all the things that can go wrong, basically, which is also has its educational purposes, I guess. So let's delete that again. So we are back to just after the log transformation, and now the first thing we do is we realize that these names, these columns, are really very chunky, and repetitive. So we want to cut them down to be a bit more useful, basically. So basically, this LFQ intensity, and then OB3, and that's probably Eva Keilhauer here, and so on. So all of this is repeated in all of the names, right? So it has no information at all. So let's remove that. And you do remove this by renaming columns, which is probably in rearrange. Yes, rename columns, and you can do this again the hard way, or you can do this with regular expressions, right? So let's try to do that with regular expressions because it's so many. And so what do we do here? So we say, I think everything up to this, what was it called? Target? No, final. Everything up to this final should go away. And that you do by dot star. And now final. Underscore, and now you want to have the thing that you want to keep. That's always parentheses. dot star. Right, so that means basically match everything, and then final, and now in the parentheses comes what you want to keep. And you see then down here actually what is the effect of applying this regular expression to the column names, and you see it's exactly what you want. You get rid of the beginning, of the repetitive beginning. Right? So let's do that. So now you have nice column names. And now with these nice column names we can define the groupings, right? So let's define groupings. That was in annotation rows. Where was it? Yes, of course, categorical annotation rows. Create from experiment name. And it's this scenario where all the names end with underscore 01, 02, 03, and so on. And we can call this also something. So that is basically the bait grouping. Press OK. Okay, now we have a nice grouping here which separates all the quadruplicate groups, right? So what are we supposed to do actually? So that's a type. That's of course not modifications, but it's interactions. So that's a typo here. We filtered, we logarithmized, we renamed, we groups, and now we are ready to filter for the valid values. And so the way we want to filter it here is that we want to keep those rows where you have good quantification for at least one of the quadruplicate groups, right? Because, I mean, that's all you can require, because like some unique interactor might actually be only quantified in one of these groups. So we require, you could say now it should be in all of the 4 or in 3 out of 4. And so what we were asked to do here is to require to have quantification in 3 out of the 4 replicates. So let's do that. Obviously 4 out of 4 would be a bit more stringent. So then we filter rows again. Filter rows based on valid values. And we want to have 3, but not in total, but in at least one group. So let's do that. And the grouping is already selected correctly. There's only one grouping. So. And values should be valid. And we reduce the matrix now. So then we do that. And we go down from 2304 to 2085. Right, so now we have the matrix that we want to work with. And we could already look for if the data is okay, looking good, for example, by looking at the histograms of the intensity. So maybe let's do that. The histograms are here. Do all of them. Maybe let's make the space a little bit bigger. So that is basically the step where you really want to sit at a big desktop monitor. That's much easier than on a laptop. But let's try to do our best here. So maybe let's decrease the size a little bit. And okay. And it looks like so in general it doesn't look bad, right? So all these histograms look very similar. So there are no major problems, normalization problems in the data set. So if you would observe at this point that histograms are very different, you would have to think about here, well, now then there are many scenarios. It could be that the data is just bad, basically, or some samples are just bad and then not recoverable. But most often it's more like the case that you see things are shifted against each other And so let's say you would see that the histograms would be shifted against each other here. You would have to do some normalizations, for example, shift all the medians of the distribution to 0 or something like this, right? But that doesn't really seem to be the case. Actually, they do look quite similar, all of them, right? So then we could just go ahead, and so the next step would be to impute so there's still missing values in there, right? Because the filter was require good measurements in at least one group, which means there's still missing values left. And these missing values we do want to impute now, so that they actually are used basically in the t-test that we're doing on these, right? So then let's impute. So that's here, imputation somewhere. And we replace missing values from a normal distribution. And I think you went over that already, right, in proteome, that this is basically saying, okay, we want to replace missing values from a normal distribution that is chosen in a way that it's basically simulating what are, the noise, the signal noise boundary, basically, so that basically the values that are added, that they're ending up on the left flank of these histograms, basically, right? Because for label-free data, it's always a good label-free protein level data. It's always a good assumption that if a value is missing, it's because it's low abundant. It's always a good assumption here. So then what we do is we replace missing values. Basically, it does now calculate what is the mean and what is the standard deviation of the values that are there. And then what it does, it then creates a normal distribution which has 0.3 width of the width that this distribution has. So you squeeze it a little bit, and you shift it down by 1.8 standard deviations. Right. So let's see what it does. Okay. So first of all, now you end up with a matrix that has only valid values, as it should be after imputation. And then let's have a look at the histograms again, what it did to the data distribution. All right, so you have a little bit more of a left tail, but you can then also highlight what the imputed values are. So that's what they are. And so it looks very reasonable in the sense that so all the imputed values are exactly on this left flank where it's supposed to be, because we assume that they're missing because of low abundance, which is a good assumption. Other thing is, so it also looks good in terms of the fraction of the imputed values is not so huge, right? So this is like, I don't know, 10% of the data or something like that, it looks like. So that's not going to disturb your data much, basically. And so in general, it looks good. However, there's this guy here that doesn't look good, right? So we already found one outlier that looks really different from the others. So we should have an eye on this, right? So maybe we can do some other things with the data. For example, I think we're asked to cluster it also. So we were looking at the histograms already. So let's do some clustering on it. This is, just exploring the data. This is not yet really creating the interaction network, but so that's one thing you should always do. You want to look at your data, right? Even if the final analysis doesn't need any clustering, it's always a nice thing to do, or principal component analysis. So all of these things give you a good overview of your data. And you might actually realize that there are quality problems with some of your samples, right? So this is actually basically the next level of quality control, that you look in an exploratory way into your data, right? And we already found, by just looking at histograms, we found actually one sample that did have a problem, right? So then let's just continue with that and do some clustering. So that's here. And so just Euclidean, so we'll cluster rows and columns and see what we get. Takes a few seconds. There it is. Okay, and then you see, so these are the samples here, these are the protein groups, and you see already among the samples there's one big outlier, right? So if you zoom in a bit, see that this guy here is really not clustering with the other guys. So what is P his 3201, and which one was the odd one out in the histograms? Probably the same. Oh, that's not the histogram. That's this one here. So if you can read, if you have good eyes, you will see that this has the same name. So that's the same sample. So it's outlier. When you look at the histograms, it's outlier when you do the hierarchical clustering, right? So that's already confirming that there's something wrong with this guy. Then one could also now look at multi-scatter plots, right? This is basically the scatter plot as you know it, but not just between two samples, but you do it between all the combination of samples, right? So let's just do that. Right, looks good in general, and so I think that's what you already saw in the clustering. So superficially, all of these pull downs look the same. I mean, that's what you saw in the heat map already. So in the heat map, if you don't do z-score or something like this, then they all look the same, which just means that everything is actually dominated not by the interactors but by the background, basically, right? And that's the same everywhere. So that's why this is so homogeneous here, except for the one where something went wrong. And so that is reflected in the multi-scatter plot as well, that most of them are actually clustering nicely around the diagonal, if you look at them, right? So you can also select one of these and you see it in large here. So, but let's see if we also have outliers here, so outliers would be things that look very odd compared to the others now, as usual. So far, so good. Nothing special. Oh, what's that? This guy here looks odd, right? So the whole row looks odd. So there's some second population visible in the plot down here. And so which one is it? So it's actually again the same. So now that is the third evidence that there's something wrong with the sample. So one may or may not, standard thing would probably be just to exclude it from here from the data analysis, which means that one of your quadruplicate groups is now a triplicate group, which is fine. You can still use it for statistical testing. So that's also one reason why it's always good to have quadruplicates instead of triplicates, because then if one of them shows this kind of behavior, you're still left with three. And with three, you're in business with statistics, basically, right? So, okay. So then, but let's leave it in for now. So, yes. Yeah. So I think in all expression proteomics examples, you would do that. You would not do it so much for pull downs, because here, like the intensity information itself carries actually a lot of information, because that is actually telling you if it's an interactor or not, basically. So you don't really want to do the z-score for pull downs, but actually for all kinds of other situations you want to do it, because then you're typically looking for proteins that have similar profiles, but then independent of the scale, basically, right? So that are reacting basically in a similar way, but it might be on completely different expression levels, and also the amplitude might be completely different. If they show a similar profile, they have something in common, right? So for all expression proteomics purposes, you would first do z-scoring of rows. For pull downs, you wouldn't, because then you actually delete exactly the information about if this is a good a clear interactor or not, basically.
Regarding the imputation, can you explain what the difference is if you did it via the total matrix like you did versus separately for each column?
Yeah, exactly. So So it's pretty much what the name says, that so if you say total matrix, then you would calculate this normal distribution based on all values in the whole matrix. While if you do it by column, then for each column you would actually calculate the normal distribution separately and would impute separately. So usually, so if everything is normalized well, then it shouldn't make a big difference if you calculate that based on the whole matrix or on single columns. And that should be the case, right? So either there is anyway, everything is, doesn't need, so everything is going well, you don't need normalization as it is here, or you need normalization, then you should do the normalization also, right? And then it makes basically no difference if you calculate the normal distribution on all samples or on samples separately. Okay, so we're ready to go ahead. So you could now exclude the suspicious sample here, but I think we just take it along now, and we basically in the end, if it should, I mean, it anyway should not appear in results because it's a negative control. But if it would appear in results, then we know that this is the wrong result, basically, right? So,
Juergen,
yes?
we would have another question.
Yes.
As opposed to a pull down, suppose they were doing an organelle isolation plasma membrane or something like that, and they have contamination from the rest of the proteome in a few samples.
Yeah.
Then would you, you would just want to find those on a gel and throw them out and not include them. But if they got into your data set and ran over your column and everything, you'd get a huge amount of very narrow dynamic range in some, right? And a much broader dynamic range for the others, but lower count. So you'd normalize over the whole data set.
So you mean if you have like an organelle specific background? So because you did some.
You're hoping to have
fractionation or something.
Organelle specific proteome,
yeah.
Right? But there was contamination in a few samples. There was contamination from something from the rest of the cell line, right? And
on top you do these pull downs, or so you do some organelle? Okay,
no, that was
a
it.
Different topic basically. So yeah. So well. What can I say? Now you have contaminations in one of your organella pull downs, and I mean, this would also then do t-test against something else somehow. I mean, what would be your control samples? Would it also be the remaining organelles, basically, in this case?
Control samples would be organelles with no treatment. The same organelles. But
okay. Treatment, no treatment with exactly the same kind of organelle, basically. And then with the treatment, you have a contamination, and without the treatment, you don't have the contamination?
Hopefully you never have it. But
yeah, hopefully never, but then...
in some cases, you do have the contamination, let's say, with the treatment. And
yeah, so let's say the contamination you have... I mean, it would be good if the contamination is reproducible, because then they wouldn't show up in the t-test, right? So if you... I mean, one should somehow randomize this in a way that the contamination are not systematically correlating with the treatment, right? I mean, but that's the general statement. So as soon as you have that, your base, I mean, sure, do it again, basically, throw it away, right? But so if you randomize it sufficiently, then that should hopefully not happen. And then if you have contamination or not, shouldn't really make a difference in that case. So, but I guess that is a general rule. As soon as your mistake that you're making somewhere is correlated with your experimental design, you're in trouble, basically, right? And there's also not much one can do then. So, okay, so I think we are ready now to go to the main step, which is now to calculate the interactors from the data. So we have massaged the data sufficiently enough to be able to do that now. And this you do here with this Hawaii plot. So we open that. And so you have to tell it a couple of things. So where does it find gene names? Then what is the grouping that we're working on? And so that can actually be much more complicated than the thing that we have here, because you can also specify with the grouping specific control groups for each of the baits. But we don't want to do this here, because we always use the complement basically as the control group. And you could even have a treatment on top so that you do pull downs with different treatments also, right? So all of this is accommodated here. But we have just a single annotation row. And so so the sample grouping is by the column that we called bait already, right? So that is actually the bait grouping basically. So we keep that here. And now we have to say what the negative control is. And this is actually, you have to scroll down completely, it's the complement. So it's not a specific group in the data. There's no control group that we want to use, but we use the complement always, right? And so then there's also some correlation with the bait calculation happening in the background. So it's basically to rescue interactors that you actually would not find in the volcano plots that you see, basically. So just leave it as is. And then what you can do is now, you can now define criteria for determining interactors. And so you can see there are actually two windows here where you can define criteria, and that's because we can define two classes of interactors. Like class A would be the clear interactors, so that would have like an FDR of 1%. And then you might want to still look at interactors or candidate interactors that are not so clear, right? And so you would use more loose criteria for this. So for example, 5% FDR, right? So with these settings here, class A would be 1% FDR, class B would be 5% FDR, and the S0 value we leave at 0.1. So then one can wonder, okay, what should I put for the S0 value? So we have here default value 0.1, and since we're always using more or less the same technology, right? So data coming from Orbitrap with the same dynamic range always, and LFQ as an algorithm, there's no reason why this should actually change all the time, right? So my recommendation would be just to leave it at the default values, and that's it. So let's do that. And now it's calculating, so it takes a bit because it has to do all these randomizations from your permutation-based FDR calculations. But hopefully it shouldn't take too long. Are there questions already while it's running? There's a question over there.
If you go through a series of analyses and then you discover after you've done all the analysis that you actually have an outlier and you remove that outlier, will it recalculate all the other analyses that you've done before removing the outlier?
No, that's not what we're working on. So that's what would be called re-executable workflow. So that's at the moment not happening, but that's something that's on the to-do list with very high priority. Yeah. And of course, you probably read your journal requirements and so on. So you're actually required to say that you have done. So when you take out this one replicate from the quadruplicate, you're required to say this, right, in your publication. But you know this, of course, that you have to do this, right? Okay, so it's done. So the Hawaii plot is here. So Hawaii has many volcanoes. That's why it's called Hawaii plot. And you see now for each of the baits that were in the data set, you see one volcano, basically, and you can also then click on one of these, and you see it then enlarged here. And also here you can then, for example, select points and things like this. So you can, for example, now, so this is for APC2. This would be the clear interactors of APC2. Then there's one in the twilight zone between 1 and 5% FDR. So that would be your class. So these would be your class A interactors. This would be the class B interactor. And so you can do lots of things here. So you can, for example, select all your class A interactors of APC2 and see where they appear in the other volcano plots, right? So you see that's also interactors of APC1, many of them, for example. But otherwise they don't appear much. So that's a nice thing here, that you basically can immediately in one view see for all of the for the whole data set that you did, where a certain protein class, for example, the interactors in one volcano plot are appearing. But you could also make the selection independent of what the interactors are. So you could also load categories with all kinds of properties of the proteins and select them here. For example, you could come with a list of known complexes or something like this, and then go and do your selection according to that, right? So that gives you very nice quality control again over your pull downs. Yes?
One question, independent of the interactomes. Is this feature available in other plot types, like multi-view plots? Like?
Yes, it is. So for example, in the multi-scatter plot here, you have the same. That you can select any of these. For example, this problematic one, and then whatever you select here, you see in all of the plots. Right? Yeah. For the histograms, I'm not so sure. Yeah, of course. So here you can. So we haven't loaded any categories, right? But if you would select category here, you would see the selection in all of the histograms. Yeah. Okay, so we can do lots of things here. And actually most of the, so you also have plot-specific information here. So here's a table with all of the plots. Yeah, I mean, here you can then also click around, and so you have information on all kinds of levels in these tables here. But now you want to go on and define your interaction network from this, right? And this you do by going to here to the network tab. So if you haven't noticed, you can switch here between matrix and network. So in matrix you have all the commands that are operating on matrices, obviously. But now we want to create a network from this here, and this is this pull-down network tool here. Sorry. No. What you have to do is, so first you have to create a network from this view of so what we are this Hawaii plot is basically a view of a matrix still, right? So now we first have to get a network out so that we can perform network commands on this, right? And so the way we get the network out is here, this button, create network from significant interactions, right? So then let's just do this. Again, we get some options here, and defaults are good. So use only enrich. So use only right side. So that means so use only in the volcano plots. Only use the right side of the volcano. Obviously, if you have something on the left side, that is not an interactor, right? That's even worse than being somewhere in the middle. Basically, that's going in the wrong direction. So that one should always check. Remove bait edges. That's more like a technical thing. That so the bait is always in there, and bait you see or you don't see as in the volcano plots. And if you would see it, then you would put a second. It would put an edge that just goes from the bait to the bait itself, and so we don't want that basically. And you can define this class C interactors here, but we didn't really do that. So let's say OK. And now we have network collection here. So network collection, as the name says, is basically a container for containing many networks, but in this case it's only one. It's the interaction network that we derived from the pull-down data. And so as networks are, so you have a node list and you have an edge list, right? So the nodes, that's basically all the baits and all the interactors that were found, so class A and class B. And then edges then is saying, so what is interacting with what in this network, basically, right? And so that would already be, that's already actually the network information. So now you have the interaction network, you're done, basically, right? But you can also view the network information here. Right, so that's basically giving you a representation of the interaction network. And yeah, that's it. So that's what you wanted, basically, right? So basically from quite big pull-down data sets, it's now actually pretty straightforward to get to figure 1 of your paper, basically. Any questions to that?